Well, I am so excited to be here today with Mark Jeffery of The Last Theory, which is a new YouTube channel looking and exploring Stephen Wolfram's ideas. And I just happened on it accidentally, and I'm completely hooked. And I wanted to introduce Mark to my viewers because, as you know, we've been very interested in Stephen Wolfram's ideas here as well. And Mark has many other irons in the fire, including the open web mind, things made thinkable, tangled web, cuckoo maps, good wood globes, the quit work podcast. And he's the author of 3 books, The Human Computer, Losing the Plot, and Out of Your Mind. And just for a second here, I'm going to share screen and show Mark's, well, and then wouldn't you know, let's see if that works. Show Mark's page. So can you see that, Mark?
Yeah, I've got that.
Yeah. Okay. So it's markjeffery.com, and this lists all the different things that he's involved in. So if you're interested in any of Mark's other work, just check that out. And so just to get started, Mark, I was hoping that you could give me some background on your life, how you came to being interested in Stephen Wolfram, and how you came to be interested in all these other things that you're doing. I mean, what order did they come in, and in what part of, you could go back to even growing up. How did you grow up, and what caught your eye? What grabbed your interest? I don't know if you've checked out any of Jordan Peterson's work at all, but
I'm familiar with a little of what he's done, but yeah, not much.
He talks a lot about how for every person there's a little glimmer out in front of them that's kind of interest. What it is that catches their interest, and that thing is what leads people forward on their path in life. And he likens it to your future calling you forward. So I was kind of wondering, when you were a child, did you see your future calling you forward? And maybe you could talk a bit about that part of your life.
Well, that's a lot of questions. First of all, thank you very much for inviting me to come talk to you on your channel. I really appreciate that, and I really appreciate your interest in The Last Theory as well. I know you're fascinated by Wolfram physics as I am, and there's a lot to discuss there. But yeah, to answer your question, I don't think I knew when I was a child where I was heading or what I wanted to do with my life. I had all sorts of ideas of what I might want to do with my life, but there was no one thing. And I think a lot of people are like this. Some people are very lucky to have one single idea of what they want their life to be, and they follow that idea and it works out beautifully for them. And that can make for a very good and focused life. But for me, and I think for a lot of other people, it's a matter of experimentation. And I think that kind of is part of why I've done so many things. I never experimented as much when I was younger as I have done as I've got older. And so I'd really recommend that young people experiment a little. There's such a set path to kind of going through high school and then university and then getting a job and following a career. It's very easy to follow one idea and not experiment and not find out that there are other ways that you might want to live your life and try different things and find out that one of them really fits you.
Well, so what did you get interested in first? What was your first experiment?
So I guess the thing that I'm working on now that goes back the longest time is the open web mind. So that stems from my interest in artificial intelligence when I was at university and after university. I've long worked in software. I've done a whole bunch of other things with my career, but there's been a lot of work in software. And back then, artificial intelligence was not going anywhere the way that it is today. Today, the applications of artificial intelligence are extremely lucrative. People who learn about artificial intelligence can get extremely good jobs in artificial intelligence because there are big tech companies who have a lot of data and can really use the pattern matching that the machine learning can give you. I was interested in it more from an academic point of view, like, what is intelligence? What is not just intelligence, but all of the other things that make us human. So what is creativity? I think that's an essential part of being human. What are emotions? I think emotions are essential to intelligence. Our emotions drive us and tell us what we want to think about and what we want to do in the world. So I think that's also extremely fundamental to what we are as animals and as human beings. And what is consciousness? That's an even deeper question, which again, I think needs to be answered. If you want to answer the question of whether artificial intelligence is possible, whether computers can be truly like humans, you've got to sort of ask that question. What is consciousness? Is there something special going on there that you couldn't reproduce in a computer on silicon? Is there something special about the way our brains work that you couldn't put into a computer program? I don't think there is, but these ideas fascinated me. And so I did some experiments on my own very low-powered personal computer back at the time. And I got it to the point where I was more interested in the philosophy of it than I was in actually making machines be like humans. And so I wrote a book about it. That was the Human Computer. It's a very long ago book now and long out of print, but that was the inspiration for that book. And after I wrote that book, my ideas were more along the lines of not how can computers be like humans, but how can computers help humans? How computers augment human intelligence rather than replace human intelligence? And so that's where the idea for the Open Web Mind was born.
And are you at a place where you can talk about the Open Web Mind, or are you keeping that secret until you launch?
I'm very happy to talk about it. Yeah, it's one of those crazily overambitious projects that is going to take a long time to get it to where I want it to be. But talking about it is fun regardless. So yeah, the basic idea behind the Open Web Mind is that it's going to be a protocol for sharing human intelligence. So as I say, I'm less interested these days in artificial intelligence. I think artificial intelligence is very useful for things like pattern matching and getting self-driving cars to drive along the road and getting images classified on the web, which is how it's used today. Those are kind of very technical applications of artificial intelligence. I'm far more interested in what humans can do on the web. So an excellent example of this, one of the best ever projects on the web, is Wikipedia. Wikipedia, there's no artificial intelligence there. It's entirely human. I mean, there are bots that run on Wikipedia to do cleanup tasks, but fundamentally, it's human beings going onto Wikipedia pages and sharing their knowledge. And the result is incredible. I mean, the amount of time that people spend looking stuff up on Wikipedia, everybody said at the beginning that it would never rival traditional encyclopedias because it's never going to be accurate. If anybody can go in and edit it, then it's not going to be accurate. But Wikipedia's proved them all wrong. You can get some of the most reliable and deep information on the internet from Wikipedia. And very often, I mean, you search for almost anything these days and the Wikipedia page comes top in Google because it provides the best introduction to any one topic. The one drawback, I think, of Wikipedia is that it's in the English language or the French language or the German language. There are many, many Wikipedias in many, many different languages, but it's in human languages. And that has great benefits in that you can just go in and read it, which is fantastic, but there's not much more you can do with it than go in and read it. Whereas if information were stored in more of the way that it's stored in the human mind, which is kind of connections between ideas. It's not, if you look inside the human mind, you don't see a Wikipedia article, about a particular topic all listed out in the English language. That's not the way the brain works. The brain is connections between neurons, and those neurons may represent, photons of light hitting your retina, or they might represent higher level ideas. But either way, it's connections between things that physiologically is the way the brain is set up. And I think we can do amazing things if the web were set up in that way as well, if instead of storing information as an article in the English language, as most of the web is, we were able to take that information from humans, not artificial intelligence, but human intelligence, and encode it in a way that you could use different controls, different interfaces, different views, even computers via APIs to navigate human knowledge and to find those connections between things. And a lot of those connections are already kind of encoded in Wikipedia. You've got links between pages, for example, which are connections between ideas, but it's still not a very easy way to navigate it. And so I'm interested in coming up with a protocol that's very simple, that just says, okay, we're going to encode connections between ideas. And these ideas aren't even going to be represented initially by words. They will be translatable into words in the English language or any other language in the world. But the fundamental structure of the knowledge is these connections between ideas. And what that'll allow us to do is play with those ideas. Instead of simply being presented with the ideas on that Wikipedia page as an article, we'll be able to move between those ideas, play with them, visualize them, and do a whole lot more with them than you can do just with the English language.
Well, so this is very exciting to me, because what I've been doing for the last 4 or 5 years probably is letting my mind work kind of like a bot on Google. Trolling through ideas on YouTube and Wikipedia and on the web and in books and so forth, because there's a certain pattern in my mind that of a way that I see the world that I think is valuable, at least it's valuable to me. And I've been trying to understand, what parts of my pattern are correct, what parts are incorrect, what parts might be useful to others, what part might not be useful to others. And so I've been navigating all these various ideas. But the thing that makes it very challenging is that YouTube is not set up to easily connect from one YouTube video to another YouTube video. So I might find something that is of particular interest to me about pattern matching, let's say. And I hear Dr. Michael Levin talking about pattern matching in cell biology, and I hear Wolfram talking about pattern matching in his theory, and then I hear some religious thinker like Jonathan Pageau talking about pattern matching in the metaphysical sphere. And I would like to be able to keep track of where all those things are, right? Right now, in order to do that, I have to write out the name of the video, and then I have to write out at what minute this thing occurs, and then I have to save that video someplace. I mean, I'm just inundated with this stuff. And if there were some easy way to just have some alphanumeric system where you could just grab this little code, this is where that occurs, or even if you could have some bot that would scroll through all the YouTube video transcripts and pull out every place that pattern matching shows up. It would be so great. Or if you could improve the way transcripts are done on YouTube. I mean, all of those things would be fantastic.
So this is very exciting, because you only need to get into, scrape the surface of the way people use the web, and you hear exactly what you're saying, those kind of things. So there's a few things I'd love to talk about in what you just said. First of all, what YouTube does to try and show you the videos that it thinks you're going to like is it uses artificial intelligence, and it sometimes gets it right, and it recommends a video which you think, oh, I never would have thought to watch that, but actually that's an amazing video. And sometimes it gets it wrong, but it doesn't give you the power to do what you want to do, to search the ideas that you want to search. It's like, it's going to tell you to, it does its best to tell you the right thing, but it tells you. It's not you navigating YouTube, it's YouTube leading you,
colonizing my brain.
Exactly. So yes, I don't think that's the ideal way to navigate the web, and YouTube is one example, Google's another example, Facebook is another example, Instagram, Twitter, all of these systems use artificial intelligence to lead you down the path that they want you to go. And I think that denies human agency. When we think in our own minds, we don't have some central authority telling us where to go. we're able to kind of, explore whatever different direction we want to explore. And I would like the web to be more like that. The other thing that I wanted to pick up on in what you just said is that your mind is unique and you have very particular interests that the people who follow you on YouTube are also very interested in. Wouldn't it be wonderful if your viewers could tap into your online mind? So if you were able to do what you want to do and navigate YouTube the way you want to navigate it. So for example, as you said, exploring pattern matching, but within the context of the people that you are very interested in and like to follow and think have something interesting to say about pattern matching. So if you were able to kind of, create a path through YouTube or a path through human knowledge based on your own personal interests, in the open web mind, you would be able to share that with your followers. So your followers would be able to subscribe to your mind and follow the things that you're interested in. And they wouldn't just follow you. They might follow Stephen Wolfram. They might follow Jordan Peterson. They might follow their friends. So when their friends discover a new podcast or a new YouTube video or some new area of knowledge that they'd never even considered, it would be more likely to show up when they navigate through ideas in their own mind.
Well, one of the other advantages that I see to that is all of the thinkers that I listen to, they each have their own mind and their own ideas and their own research. But oftentimes I can see very clearly, this person should be talking to that person. They have some very interesting overlap that they're not even aware of. But the problem is, even when they do talk to each other, each one is in his own silo, and he doesn't understand what the overlap is or why this other person has something interesting to tell him. So they're each just kind of, this is a pejorative, but they're each sort of spouting their own ideas, and they're not really learning from each other.
Yeah.
Now, one of the few people that really works at trying to learn from the people that he talks to is Jordan Peterson. He really listens carefully and tries to understand what it is that they have that they can offer him. But some of the other people don't realize that there's a whole treasure trove there for them that would fit into their world. And if there was some easy way to summarize another person's main points that fit with this guy's main points. Like Stephen Wolfram should definitely be talking to this biochemist by the name of Michael Levin. No question, those two should be talking. And I've had a couple of email exchanges with Michael Levin, and he realizes that he needs to talk to Wolfram, but I can't get hold of Wolfram. So, But even if they were talking, I'm not sure that Wolfram would understand why he needs to talk to Michael Levin. And so, but if I could summarize, if I could, make little brief clips of this and this and this idea, and then hand that to Wolfram and say, here, this is what you need to look at before you talk to him. And vice versa. Then when they talk, it would be much more fruitful. They would understand each other much better, right?
Well, if you find a solution to that problem, I'd love to hear it, because I think that's one of the most fundamental problems of our times, is getting people to talk to each other when, not even when they just disagree, but when they're just coming at things from different points of view. It's super fruitful to be able to talk across those academic boundaries, for example, and it's super fruitful to just hear ideas that you wouldn't otherwise have thought of yourself. So,
well, that's part of what I try to do on my channel, is get them talking to each other, even if it's only this video and that video, and then comparing the ideas, right? So there were a couple of things I wanted to show you today from Stephen Wolfram and related to the Ruliad. But before I do that, I wonder if you would like to just briefly explain what it is that you're doing on the last theory and what inspired you to start that YouTube channel.
Yeah, absolutely. So like you, I'm fascinated by Stephen Wolfram's ideas about physics. So I kind of gave up on physics after university. I did study physics at university. I'm not a physicist. After university, I kind of lost interest in physics. Was
your undergraduate degree in computer science?
No, it was actually in physics.
Okay. And then you
This
went
was,
into computer science after
yeah, that's
university?
right. Back in these days, particularly in the UK, where I'm from, there weren't really any well-developed university courses in computer science, and so you could do it, but it wasn't something people did, and yet people wanted to employ software engineers. So very often you got a degree in some mathematical or scientific subject or any subject, and then went into software development afterwards. So that's what I did. I was fascinated by physics before university. Unfortunately, the course at university managed to kill that interest in physics. It didn't really cover any of the more exciting ideas about physics that got me interested in it in the first place. You know, the ideas of quantum mechanics and relativity, and so I also wasn't as good as physics as I think I would have needed to have been to carry on doing physics. I mean, I could have carried on and done a PhD, but I just wasn't interested enough in it. I just didn't think it was going to be my thing. So I was kind of disappointed in the decades since then of what physicists were doing. That the theories that were coming out of physics over those next decades seemed to be just getting ever deeper and deeper into mathematics and ever more complicated, and the antithesis really of what a good theory of physics should be. So, I mean, you know, my ideal of a good theory of physics is Einstein's general theory of relativity. It's not easy to understand. You know, the curvature of space-time, that's kind of pretty mind-blowing. And so it's not simple in the sense that you can just look at it and understand it. But it's simple in the sense that once you get those basic concepts, it, it explains so much. It explains how gravity works, not just on a local scale, but across the entire universe. It explains cosmology, it explains black holes, it explains the curvature of light as it passes by a massive body in very simple terms. You know, just this one concept of the curvature of space-time reveals so much. And what physicists seem to be doing is the opposite. They were getting very mathematical. Einstein famously didn't really like mathematics. He did use it, and he wouldn't have come up with the general theory of relativity if he hadn't gone into it deeply. But he was coming at it from the point of view of the concepts, and it seemed like physics had switched to we didn't have any big ideas anymore in physics. We just tried ever more complicated equations to explain ever more anomalies in what were becoming extremely complex theories. So I kind of just lost interest. I was more interested in, you know, what would happen if you had a very simple theory. What if you kind of got down to basics and thought that, you know, what is there in physics? There's events that happen in space and in time, and there's connections between those events, and this thing here affects this thing there. And I played around with ideas in my head about, you know, how that would look, but never went anywhere. And then a friend of mine told me about Stephen Wolfram's ideas, and I had a look at it, and I thought, yes, that's it. That's it. That's one, what I was thinking, and two, oh, this guy has gone way beyond that. Now, I still haven't got deeply enough into Wolfram physics to be able to validate any of his claims, but I'm looking into it, and his claims of being able to explain special relativity and general relativity and quantum mechanics, and crucially explain general relativity and quantum mechanics in the same theory, and the simplicity of his ideas that are more on the level of Einstein's general theory of relativity than they are of any other physics in my lifetime, just made me think, okay, this looks like it. And I was sort of blown away because I wasn't expecting there to be any progress in physics in my lifetime based on what physicists were putting out there over the last few decades. And so I sort of felt a little disappointed. It's like, if only I were like young again, if I was still studying physics at university, this is what I'd be going into. This is what I would be investigating. And whether or not it turns out to be the right theory, it's so promising that this is what I would dedicate my life to. But I was never, as I say, that good at physics or mathematics in the first place. And then I realized, well, hang on a minute. I kind of know a little bit of physics. I know a little bit of mathematics. I know a lot of computer science, having been a software developer for most of my career. And I've done some writing. I know how to explain ideas in simple ways. So I thought, okay, so there is actually a role for me here. This is some pretty complex stuff, and there are some fascinating ideas in what Stephen Wolfram is putting out there. I want to write about this. I want to put out a podcast and a YouTube channel. And as I'm learning myself what Stephen Wolfram is proposing in his theory, I'm going to explain it to as many people as I can on the web.
Well, and so what you've done, I apologize, I should have brought up one of your YouTube videos, but I'll just briefly explain what it is that you're doing. You're taking one concept at a time and then visualizing it. So for me, it was very helpful when you visualized the changes from one event to another, when you showed the edges and the nodes, because as many times as Wolfram has talked about that, and as much as I've looked over the charts and the graphs and all of the visuals that he's done online, it was never really clear to me how it was that one thing changed to another. And then you did this very simple visualization of the edges and the nodes, and all of a sudden I could just see how this was working. And it now just popped into my head. A video that I rewatched yesterday after a couple of years, has to do with the quantum gravity group of researchers that are coming up with a theory where the entire universe consists of Planck-sized tetrahedrons.
Oh, wow.
Have you heard that?
I've not come across that, no.
Yeah, because when you draw the edges and the nodes, what it really looks like is a 2D version of a tetrahedron. Yeah. That change that happens at each spot is just exactly like moving from one node to a tetrahedron, and then moving, and then two edges. And so anyway, those kinds of things are very fascinating to me.
They are. If you like, Karen, I can very quickly share my screen and
sure. Let me make sure that you're approved for sharing. Should be okay.
Perfect. Let me share my screen. Oh no, it says host disabled participant screen sharing.
Well, I didn't actually.
No.
They don't make it easy, because every time I do this, I have to find a different spot of where it might be. Allow participants to share a screen. That's what it says.
Yeah, they do not make it easy, do they?
Now, it says that you should be able to share a screen. Try again.
Okay. Oh, yeah, I've got it now. You found the right button. That's perfect.
Well, I turned it off and then I turned it on again.
Perfect. There we go.
Okay, so here we are.
Okay, so this is just a simple rule here. So the way that Wolfram physics works on a very basic level, and I'm glad you like this basic stuff, because I really like it too. Stephen Wolfram goes very, very fast into some very, very big ideas, which I love. But I also want to understand it at the very basic physical level, what's going on in his universe. So what he proposes is that there may be rules like this rule here, where you have nodes, which are just points. So there's 3 points on this very simple graph here, which are connected by edges. So these arrows are the edges. So there's one edge from this node to this node, and there's another edge from this node to this node. So this is a very simple universe. There's not much going on here. But if you apply a rule to it, what the rule does is it matches some edges here. So if I just step there. So this rule at the top says you've got to match an edge that goes from one node, which we're going to label node 1, that's this node here, to a node 2. So we've got this one edge between node 1 and node 2, and then another edge between node 1 and node 3. So this is node 1 and this is node 3. So we just matched these blue edges here. It's like, okay, great, we've got our match. And then it says, okay, here's what we're going to do with these edges that we've got. We're going to delete one of the edges, the edge from node 1 to node 2, but we're going to keep the edge here from node 1 to node 3. And then we're going to create 3 new edges. So let's delete that red edge and create these 3 new green edges from node 1 to node 4, from node 2 to node 4, and from node 3 to node 4. So there we go. We've got 3 new edges. So here's our new universe. So there's not very much that happened there. We just applied an extremely simple rule to an extremely simple universe. And here's what we got, a slightly less simple universe. The strange thing that happens is that when you apply these rules, or some of these rules at least, over and over again, so let's just apply it again here, we're deleting one of those edges and creating 3 new edges. And again, we're matching those 2 edges and deleting one and creating 3 more. If we run that a few times, what starts happening is that the universe gets complex in very strange ways. And I should say I'm applying the rules slightly differently from the way Stephen Wolfram does here. And I'll get into that in future episodes of The Last Theory. But this gives you an idea of the kind of complexity that can arise from just a very simple rule. If I speed that up a little bit, you can see the universe very quickly starts to become very complex. And it's looking kind of weird. It's not looking like, a basic grid of space. It's far more complicated than that. But it seems possible that this could give rise to something that looks a little bit like our universe. So that's
okay,
a very...
Before you go any farther, I want to play this. I want to play this clip for you.
Okay, I'll stop sharing my screen here.
No, it's okay. You can leave. Well, it's okay. We can come back to it later.
Yeah.
I want to show you this video of Wolfram speaking to Joscha Bach, and just catch this minute and a half here.
Okay, and what is operating on it?
It's a rule that simply says if you've got a cluster of things that
can you hear that?
Yes.
It's not really very loud, is it? Hold on, let me try. When I share screen, sometimes it doesn't optimize. We'll try again.
Okay, and what is operating on it?
It's a rule that simply says if you've got a cluster of things that looks like this, turn it into one that looks like this. Mm-hmm. It's that rule. So the first way of thinking about this, you just say, pick a rule. It's a particular rule. Okay. We can go to another level where we're talking about the ruliad, which is a different level above that and a little bit harder to understand. But the first level is there is a definite rule and you're applying that rule every way you could apply it.
Yes. Where does the rule come from? What specifies that it's this rule and not another one?
Well, yes, then you're going...
And what executes it?
You're descending into the rabbit hole.
Yes, we have to. Please go.
Okay.
So what is operating on it? Where does the rule come from? What specifies this rule and not another rule? And what is executing it? That is the big question right there. I've had numerous conversations with another physicist who says until he can explain what is executing it, the whole theory is meaningless. And it's so funny because when Joscha Bach kind of pins him on this, he says that's going down a rabbit hole. And then he goes off talking about electrons and what electrons are in his system, because he doesn't want to talk about what it is that's executing it. He says he'll get to it later, but I haven't watched the whole video yet. So I don't know, maybe he does. But
it is
from your perspective, what is operating on it? What is executing it?
Yeah, so let's start with that first question there about why this rule, who chooses the rule, and let's get to that rabbit hole question.
Well, I know the answer to that one. At least I know what Wolfram would say. He'd say it's not a particular rule, it's all rules in all possible ways.
Perfect.
Right?
Yeah, exactly. Yeah, indeed. Yeah, I think
which isn't really an answer if there's not something executing the rules.
Yeah,
I understand that you don't need to choose among them. It doesn't need some intelligence choosing which rule to execute at which point, but it does need something, some Turing machine or something that's doing the executing of the rule, right?
Okay, so I'm not sure I agree with that. So let's get into it. This is
Okay.
so I've actually been thinking about this as my next episode of The Last Theory is to address precisely this question because I
Spoiler alert.
I've known no, let me practice my ideas on you and see how they land because this is inspired by you. You've asked me this question and it's a fascinating question. So let me try this out. I'm not sure I'm going to please you, but let's see if I can. Let's see if we can get somewhere here. So I think the place this is inspired from is that when I run that simulation of Wolfram physics that I just showed you, I am running it literally on a computer. And what is the computer that's running it is this. It's literally this computer is the one that is running that simulation.
Mm-hmm.
So that's a nice, easy question to answer. So it's obvious to ask the next question. It's like, well, okay, so if this simulation is run on this computer, then the simulation that's our universe, what computer is that run on?
Well, so hold on a second. So you're looking at Wolfram's theory as describing a simulation.
Well, let me rephrase that. So when I run it, it's a simulation.
Okay.
When the universe runs it, it's kind of the real thing. So, I mean, it could be a simulation. We might be in a simulation and there might be a computer like, in the movie The Matrix, where everything in our universe is actually being run on a computer in another universe. And that's a whole different article. I want to address that one as well. That seems possible. I think it also seems to me unlikely, but it's possible. These things are possible, but no, I used the wrong word there. I think when I run it, it's a simulation because I'm simulating our universe. When the universe runs it, it's the universe. It's reality, and so I like to go back to the history of physics when I try and explain and try and understand myself the philosophy behind the ideas we have now, because it's often very difficult to take a step back from where we are now and think, okay, well, how's this going to look in several generations, several hundred years time? And you can get an idea of that by looking back several generations or several hundred years time about how kind of physics looked to people back then. And so I like to go back. I think there's three main phases of physics. There was physics back in the days of the ancient Greeks, when most of the ideas were quantitative. There weren't any numbers involved. There were theories saying things like Earth-like things go down, and fire-like things go up. And there weren't any numbers attached to those. It was just assumed that those were the natural places of things. So when you drop a stone, it falls, and when you look at fire, it rises. And that kind of begs a question. Is like, okay, well, what makes the stone fall and what makes the fire rise? It's a very difficult question to answer, and I'm not sure. I'm sure there were varied opinions amongst the ancient Greeks, so I'm not sure what Aristotle would have said, for example, like what makes it move. And of course, there's very simple but not very explanatory answers like that. Like you could say, the universe makes it move, or God makes it move, and that begs all sorts of questions, but that's an answer at least. So then the second phase of physics is when physics started to become mathematical, from the age of Galileo onwards, more or less. That's a very rough idea of the history of mathematics in physics, but around that time, physics started to become very mathematical. Galileo was able to put numbers on things, like how fast does a stone fall if you drop it from a tower? Well, these two stones, even though they're different weights, are going to fall at the same rate. And he was actually able to do experiments of rolling things down ramps and actually measuring things. And Newton took this to a whole other level and came up with calculus and very mathematical theories of how gravity works, how motion works, for example. So if we were in the age of Newton, would we be asking, okay, well, you've come up with this theory and it's got this mathematical equation attached to it, and all you have to do is kind of, work out the solution to the mathematical equation, and you'll be able to work out when I drop this stone, how fast it's going to fall. But when I drop this stone, who's doing the calculation? Is there like somebody in the background with an abacus who's kind of doing all the calculations, like, okay, the momentum's got to go this, like this, the velocity's got to go like this. In our day, we would say, is there somebody with an electronic calculator going, okay, the square root of this? And it's a slightly strange question to ask of Newton, But it would have been a question that would have seemed less strange in the day, because mathematics was new. Mathematics was, okay, well, you say that the universe worked by mathematics according to your equations, but who's solving all those equations? Solving equations is hard. That's very strange. And again, you can come to simple solutions, like I'm sure Newton would have said, well, God does those equations. He was a very religious guy, and it's an answer, but again, it's not really a physics answer. It's a religious answer, and that's great, but it's not a physics answer. It doesn't give you any more explanatory power over the falling stone. So come to our day, I think we're in the third phase of physics, where physics is computational. And it hasn't been until now, because we haven't had the tools to be able to do physics on computers. We haven't had computers until now, just as in Newton's day, he didn't have calculus until he invented it, and Leibniz invented it. Before then, there was no calculus, so there weren't really the tools to do physics using mathematics. So now there are the tools to do physics using computers. We have computers. We're asking the same questions. We're asking, okay, so if you say that there's this computation that's going on that creates the evolution of the graph, who's doing that computation, and on what computer? Just as maybe in Newton's day, people would have said, who's doing the mathematical equations, who's solving it, who's doing the abacus calculations? And again, I think, unfortunately, we're in the same place as we were back then. I don't think there is somebody in the background with an abacus doing the calculations when somebody drops a stone. It's just the way that the universe works, and we are explaining that using the language that we know best. Newton invented a whole new language called calculus to explain the falling of the stone. And so that's the language we've used for the last few hundred years to describe physics. Now Wolfram is creating a whole new language to describe the evolution of the universe in computational terms. And so that's the language that we're using to explain physics. But the question is the same. It's like, okay, so we're just describing how the universe evolves, and we're using our current paradigm, which is a computational paradigm, to explain it to ourselves and to be able to simulate it ourselves. But what's doing the computation in the universe? I'm not sure we'll ever have the answer to that question. I'm not sure we'll do any better than Newton might have done by saying that God is solving the equations.
I certainly understand. I mean, I get what you're saying about the questions that arise based on where we're at in our, in the history of our thinking, right? But I don't think in any way that Newton was saying that because of these equations, reality manifests. But Wolfram is saying because of these computations, we go from nothing to something. So now it is perfectly possible that thought can become a physical object. We know that because you're a software engineer. You have an idea in your mind that's a thought, and then through a variety of executions, you can end up. My husband is a marketing guy for a technology company, and he comes up with an idea of some box that he wants to create that's going to do something with a lot of routers and hubs and chips in it that's going to, amplify a signal or something like that. He comes up with this idea in his head, and then he gets people to put together a lot of other ideas and parts and add the software, and voila, you've got this box. Okay. Yeah. But then you are also, you have the idea and it manifests into reality, but there are a number of steps along the way that utilize resources and that utilize design and all of those things to manifest the idea into reality. But is Wolfram saying that the computation alone, without the idea and without the resource, is enough to go from 0 to 1? I mean, is enough to go from nothing to something?
So Wolfram's theory, I think, is a description of what's happening. So his describing, okay, the universe behaves in a way that if we were running these rules on these graphs, it would produce the same result. It's the same as Einstein's general theory of relativity. What he's saying is that the universe behaves in such a way that if it were four-dimensional space-time, and if it were curved in this way by mass and energy, then it would behave in this way. And we compare what Einstein builds up. Einstein sort of starts from first principle, builds up this theory based on the curvature of space-time, and produces these results saying, okay, well, that means that light's going to bend this way as it passes the sun. And we look at our universe and we look at how light bends when it passes the sun. It's like, oh, wow, it bends in exactly the same way that Einstein predicted that it would. That's pretty amazing. Do we then take the step and say, and therefore our universe is four-dimensional curved space-time? We do think of the universe that way, but I'm not sure we should. Wolfram's theories actually separate space and time in a way that Einstein brought them together. Wolfram's theories separate them. Mm-hmm. That doesn't invalidate Einstein's theories at all. Einstein's theories, Wolfram's theories agree with Einstein's theories. And so it doesn't invalidate Einstein. It's just a different way of thinking about it. Einstein's way of thinking about it works on a very large scale. Wolfram's way of thinking about it works on an unimaginably tiny scale. And yet they're just different ways of thinking about it. What's real is that the light from distant stars curves as it passes the sun. That's real because we've seen it through our telescopes. The model we have underneath that, is it real? It's hard to say. I mean, if you'd asked me a few years ago, is space and time a four-dimensional continuum that is curved by the presence of mass and energy, I would have said, yeah, that's the current theory. That's the way reality seems to be. And yet Wolfram say, oh no, it's not like that. That's one way of visualizing it. But if you're looking at a very small scale, this is a better way of visualizing it. The reality is what we see. The models created by Einstein and Wolfram, I don't know what status they have in reality.
Well, so let's touch on what Wolfram says about space, because he says that space basically the universe is just space. It is just made of space, and space is made of all these little atoms of space, not actual atoms, not like hard little balls, but that these nodes are the constituent of space. Yeah. And that's what space is made of, and that the edges between nodes are the events that take place that when a new node is generated by the rule, then that event is time.
Yeah.
Okay. So
absolutely. Yeah.
So spring off of that a little bit.
Yeah. So what Wolfram's doing here is the same as what Einstein did, which is what makes it so exciting, because physicists haven't been doing this for the last 100 years. And what Einstein did is he started with thought experiments. He didn't start with observations and try and find a way to fit mathematical equations to the observations. Particularly as a younger physicist, he kind of ignored the observations. It's like he focused on thought experiments, like what would happen if you were traveling alongside a photon at the speed of light? What would the world look like to you? And he didn't say, okay, well, let's do the experiment, because you can't do that experiment. You can't run alongside a photon at the speed of light. It's not going to work. Instead, he thought about it in his mind, and he constructed theories from that. So he started not with the world, he started with ideas that were informed by what he saw in the world, of course, and what physicists had discovered up until that point in history. But were all in his mind. He was constructing something and saying, well, what would happen if the speed of light were constant for everybody? And how would that look from different frames of reference? And he'd work up and work up and work up and come up with a theory. And miraculously, the theory would have fit the facts, even though anybody looking at it at the time would say, well, that's crazy. You know, time works differently for people in different places, traveling at different speeds in different gravitational fields. That's just nonsense. Things can look different lengths depending on what frame of reference. That's just nonsense. Wolfram's doing the same. He's starting with a very basic theory. He's starting with his graph of nodes and edges and applying rules to it, and just starting with, oh, well, what would happen if the universe looked like this? And then he works up and up and up, and he says, well, actually, one of the consequences would be that you would not be able to transmit information faster than a certain rate, a rate that we call the speed of light. That's the fastest that we can transmit information in our universe. And so, oh, well, actually, this universe looks a little bit like our universe. So he starts with ideas and builds up from there. And so I think what he's saying about space and time is that, okay, let's start with the graph. We're starting with the idea and we're building out from there. And you can't help but look at a graph and think, well, that looks a little bit like space, doesn't it? It's like, it's kind of spread out, you can move from this node to this node. It's sort of space-like. And the way that the graph evolves looks a little bit like time. And what he's saying is he's taking one step further. He's saying, okay, well, what if this is all there is in the universe? There is nothing but this graph. And everything else, so space and time and matter, are just aspects of this graph. The space is the separation type aspect of this graph. Time is the evolution of the graph as you apply rules to it over and over again. And matter maybe is just kind of tangled bits of graph that are traveling through the graph. So they appear to us to be traveling through space, just like elementary particles. And he's building it out from there. So I find all of those ideas fascinating.
Well, when he gets to the matter part here, let's take a look at the Joscha Bach video, because there is this very cool thing where he is talking about, I think it's at 36, somewhere in there. Let's try that.
A little piece of froth on top of the main activity in the universe, which is kind of knitting together the structure of space.
Okay, what he's talking about,
piece of froth.
What he's talking about there with the tiny piece of froth that's just floating along, he's describing electrons.
Yep.
Okay, so let's go back a little bit here.
A little piece of froth on top of the main activity in the universe, which is kind of knitting together the structure of space. That is, it just like in a fluid, the vast majority of the activity is collisions between molecules that maintain the idea of a gas with pressure or liquid or whatever else, rather than the little tiny effects that make collective motions like vortices and so on. And so it is, I think, with the universe. But
so the electron is a pattern in the graph, and this pattern is the property that it's dynamic, and that's evolving. The electron is a pattern in the structure of the graph, a characteristic pattern. And this characteristic pattern is the property that it is, unless it collides with another pattern that dissolves it, it is persistent, and it's dynamic, and it is progressing through this graphical structure of space. And it is occupying a certain region in a particular.
So the pattern is persistent, it's progressing, and it's occupying a certain region.
Yep.
As long as it's not bumping up against some other pattern. And so when Wolfram was talking about the electron, he was describing it in the same way he would describe a vortex or a tornado. It's actually made of things that are moving, but they're moving in such a way that it has an existence. Yep. And that's what an electron is like. And then Joscha Bach jumps in and he says, well, it's a pattern. And the electron is a characteristic pattern that's persistent and progressing and continues through time. And I thought that was so interesting because there's this metaphysical thinker named Jonathan Peugeot who describes all of our reality as being made up of narrative patterns, that patterns exist in the world, and that those patterns are what what make the one out of the many. So for example, if you have an apple, it's a thing, right? But the apple is actually made up of an infinite number of things, smaller, not maybe quite infinite, but you could, if you divide it down as far as it can go, you're going to get down to the quantum particles and the gluons and the quarks and all of that. But if you're at the gluon and the quark level, if you were in that level, and this, I like the way Wolfram talks about the observer, because it depends on where you are in the system. If you're at the gluon and quark level, do you have any idea that there's a level above you that's atomic? Or if you're at the atomic level, do you have any idea that there's a level above you that's molecular? Whatever level you're in, you can see below you to see what it's made up of if you're extraordinarily observant, but you have no idea what it is that's above you. But each one of these levels, the only way that things consist in that level is to be unified by some pattern. So those patterns make all of this something into a one, like a cell. Yeah. There's a pattern in a cell, but the cell has a boundary, and there's a certain way that boundary has to be built on a cell, and the inside of the cell has to be built a certain way. It's a pattern, right? And then the way the cells come together is a pattern. Yeah. And then the way Michael Levin talks about it, they have a collective intelligence because they signal each other bioelectrically. They talk to each other in a bioelectric language and tell each other what to do and where to go and how to differentiate. And so all of these things are patterns. So I really like the way Joscha Bach was talking about it, but Wolfram was kind of like, what are you saying? And I think it's going to take him a while to really absorb. Now, a lot of things I don't like about Joscha Bach's viewpoint, because it seems very solipsistic to me. He's just all up inside his head, and there is no real world. But I did like his description of that pattern.
Yeah, there's a lot there. So you were talking about the different levels, and you were talking about the particles traveling through space, and you're talking about looking down levels and looking up levels and how far can you see. So just to be clear, I think the patterns that Stephen Wolfram is talking about when he's talking about matter in space is, suppose you've got like a grid in space of just empty space, and it's just made up of something like the graph that I showed earlier, but extended over a vastly larger amount of space. That's just empty space. And Stephen Wolfram said that he thinks that most of what the graph does is empty space. But of course, within that graph, you can have like ripples. You can have slight perturbances that just happen and then die out because you've applied a particular rule in a particular place, and it then changes the nature of space in that particular place, and then it just dies out because some other rule comes along and undoes it, or it just doesn't go anywhere. But there may also be persistent patterns in space where a rule is applied and it creates a certain tangle of space in that region, similar to the tangle that I was showing earlier on my simulation, but probably at a much larger scale. And the way that the rule works is that tangle persists in space and actually moves through space. And so that may be a particle. And of course, we see all sorts of particles using our particle accelerators and all of the instruments that physicists can bring to bear on looking at things that are incredibly tiny. But we can probably only see extremely large particles, extremely large perturbances in the graph that persist over time and travel through space. There's probably all sorts of stuff going on. Well, if Wolfram's right, there's definitely all sorts of stuff going on in the graph at that very lowest level that we will never see, just because our instruments will never allow us to see things at that depth. And also because those perturbances never have any permanent influence on what's happening at a higher level. And if they don't have a permanent influence on what's happening at a higher level, by definition, they can never have any influence on us, and therefore we can never see them because we are at that higher level. So there's all sorts of stuff. There's only so far we can see down. I'm fascinated by your idea that there's only so far we can see up as well. And it's also fascinating to talk about, okay, what are different ways of looking at things? You know, there's our way of looking at things. There are certain things that are of interest to us. And Wolfram goes very far in this. He says, when he talks about the Ruliad and the possibility of there being multiple different rules, and that you could interpret the universe using particular rules if you're particularly interested in one particular way of looking at the universe that might differ from somebody else's interests and how they would look at the universe through the lens of different rules. And that's fascinating stuff. This is really high level stuff now, but it is fascinating. And that sort of gets to what you're talking about here. It's like, are there other levels, other different ways of looking at things that would be incomprehensible to us?
Well, I have a couple things there. One is that when you were talking about things being persistent through time, and when Wolfram talks about that, when he gets up to the macro level and he's talking about like a human being, as we move through space, I'm moving my arm, all of the particles that in my arm are moving through space.
Yeah.
Right. And the way he describes that is that the Ruliad spends most of its time knitting things together.
Yes.
Because my arm is moving through space, it has to be continually recreated in the entire movement. Every move that I make, it's being rebuilt constantly, which is kind of mind-blowing. But then going back to the Ruliad thing and the rule thing, I want to share a little brief clip with you that I think you'll find kind of interesting. Again, it's one of these videos, but this one is Jordan Peterson speaking with Roger Penrose.
Oh yeah.
And he's been asking Penrose about the physics of consciousness. But then at this one point, Peterson is posing a question. And in this question, it sounded very much to me as though, even though he has not yet talked to Stephen Wolfram, and I think he should, I think what he's doing here basically is describing something very like the Ruliad.
Fluid or something like that. So that would be the way that mathematics drives the physics. It's general laws rather than a specific thing. I think that's
well.
That's
I'm
what
curious
I'm trying to say.
though, too, because in some sense, and I could obviously be wrong about this, but the physical reality seems to constrain the mathematical possibility, because there's only some mathematical rules that govern the behavior of actual objects, even though there's all sorts of possible mathematics that could govern the action of all sorts of hypothetical objects. Right? So imagine if there's an underlying, I can't help but think that this is associated with this many worlds idea, but if there's an underlying metaverse of mathematical possibility, you get the emergence of something like, well, what would you say? One concretized exploration of that possibility space, and that now establishes a relationship between one element of that mathematical possibility space and well, in reality itself doesn't exhaust the search space, but and it seems to me that that's analogous to this tiling problem in some sense.
So, Roger Penrose has spent a lot of his life working on the tiling problem, which is in some ways analogous to, I think, the way Peterson is seeing it. In some ways, it's analogous to the 2D version of Wolfram's universe, like a cellular automaton. But so here is the transcript of what Peterson just said. Can you see my screen over here on the left?
No, I can't. It's actually blank at the moment.
Okay, so let me see if I stop share and bring up a different screen. I guess that's what I have to do. Now can you see it?
Yep.
Okay. But the physical reality seems to constrain the mathematical possibility because there's only some mathematical rules that govern the behavior of actual objects, even though there's all sorts of possible mathematics that could govern the action of all sorts of hypothetical objects. Imagine there's an underlying metaverse of mathematical possibility, and you get the emergence of something like one concretized exploration of that possibility space. And that now establishes a relationship between one element of that mathematical possibility space and reality itself. That doesn't exhaust the search space, but it seems to me that that's analogous to this tiling problem in some sense. So that's what Jordan Peterson said. And it seems to me that there's a coherence there between this idea and Wolfram's idea, the idea that there's one concretized exploration of that possibility space. Wolfram talks a lot about where you, depending on where you are as an observer in the hypergraph or in the branchial space or in the multi-way space of the universe, that's going to affect the way that you look at the laws, the mathematical laws and the physical laws, that's going to affect the way that you imagine or draft the laws. Yeah. I mean, he always talks about how if an alien were there and an alien would be in a different part of the universe, and that they would see the laws in a completely different way because they're coming at it from a different angle, so to speak.
Yeah. Yeah, there's a lot there. We're at an incredibly high level now, and I'm sort of not sure where to begin there. Perhaps we should talk about the tiling problem very briefly. I'll try and remember this because it's a long time since I've read what Roger Penrose writes about the tiling problem. But I think, and apologies to him if I'm getting this wrong, but I think his basic idea is that there are certain problems that you cannot solve algorithmically. And one example of this that he gives is a tiling problem where you have these wonderful Penrose tiles which fit together perfectly, but they're kind of very weird shapes. So you might have a couple of these tiles, and the task of the game is to completely tile a plane with these tiles. And you can't write a computer program to solve this problem. Mm-hmm. At least that's Roger Penrose's claim, because it's non-algorithmic. And he is absolutely correct mathematically to say that there's no mathematical solution to this problem. That's proven. He's proven that. Where I would disagree with him is that I think if you introduce randomness, then it's perfectly possible to write a computer program to tile the plane in the same way that a human being would tile the plane. So Roger Penrose's claim is that there's something strange about consciousness that allows us to work on this tiling problem, and a computer can't do it. But he's thinking of a computer traditionally programmed, without any randomness in the program, without any of what AI researchers would put into the program these days. If instead you use a computer that works more like the human brain, so using the kind of programming that an artificial intelligence researcher might use today, when a human does this problem, we do it by kind of trial and error. We don't have the perfect mathematical answer any more than the computer does, but we try putting a tile here and a tile, oh, that doesn't work, and so remove the tile and put a different tile there, and that works. And we slowly kind of work our way across the plane, and given an infinite amount of time, maybe we could tile an infinite plane. But we're not doing anything special. We're doing it by trial and error. We're introducing some randomness there. When we do something by trial and error, we say, oh, try it this way. We're not picking an algorithmically determined way to put it down. We're just trying something randomly. Okay, great, that works, that doesn't work. You could program a computer to do exactly the same thing. Once you introduce randomness, then I think Roger Penrose's arguments that it's algorithmically impossible break down, and that it becomes possible for a computer to solve this problem in the same way that a human being can solve this problem, basically by trial and error. So that's where I disagree with Roger Penrose about the possibility of consciousness in artificially intelligent computers. It's an old argument. So what I'm kind of trying to work out here is how Jordan Peterson thinks this applies to kind of ideas of Wolfram physics.
He's not applying it to Wolfram physics at all.
Okay.
No, he's just talking about, he's trying to understand. Okay, so Jordan Peterson sees the world as basically a narrative.
Okay.
Not as a computer construct, or not even as a mental construct, but he sees the world as a narrative. And the book that he wrote over the course of 15 years back in the late 80s, that was published in 1999, called Maps of Meaning, lays out this narrative structure. And at a very simple level, it is, I am here. I see that I could get over there, and I want to go from here to there.
Yeah.
And something happens in between.
Yeah.
Okay. Often what happens in between is some anomalous event.
Okay.
Okay. And, maybe the anomalous event is something good, maybe it's something bad. Whatever that anomalous event is affects the trajectory that I take to get from here to there. But even before you start talking about the journey, you have to talk about why do we even go there?
Yeah.
Because we go there because it looks better than here.
Yeah.
Which implies that there is a value structure to the universe. There is something better than this, which means that there has to be better and worse built into the structure of the universe.
Why does Jordan Peterson ascribe that value structure to the universe rather than to ourselves? I can fully accept that we have a value structure. We decide we want to go over there, and so we, according to...
Well, I mean, if you take it all the way back to the beginning of life, the simplest cell has to be making that trajectory all the time.
Right.
And if you look at evolutionary theory, the idea, I mean, obviously we have 3.8 billion characters in our DNA, but the very earliest cells maybe had, I don't know, 100,000 characters. Even the simplest cell has a lot of information packed into the DNA, and how that got in there, that's another question. But let's just assume that somehow this cell arises with this information in it. How does that amount of information grow into this amount of information? And in my mind, the way that must happen is that it's moving along through space and time, and an anomalous event happens that it has to adapt to, and in the adaptation, it increases the amount of information that it has.
Yeah.
And that information epigenetically eventually becomes part of the DNA and becomes heritable.
Yeah.
That's the only way it could possibly happen. So in other words, even the simplest cell is operating in a narrative structure where there is some value structure. And there's a guy named Mark Solms who wrote a book called Journey to the Source of Consciousness, where he's a neuroscientist and a cognitive scientist and all that kind of stuff. And I had a long talk with him, and his concept is that the only way to maintain homeostasis, even in the simplest cell structures, is that they have some sort of a value structure. I'm hot, I need to get cooler, otherwise I'm going to stop living. Or I'm hungry, I need to find food. So that is better than this, therefore I move, therefore I act. So the only thing that causes action is this value structure that's built into life, at least life. Well, pre-life, then that's another question. But the narrative structure of life is that there has to be a value structure. Now, we're almost at your limit. You said you had an hour and a half limit. So
yeah,
I don't know if you want to continue down this road or if you want to explore this in another episode.
Well, perhaps I can, I'd love to come back for another episode. These are fascinating topics. But perhaps I can just respond to what you just said. I think this might come back to ways of looking at things, ways of explaining things, ways of describing things. So, for example, let's go to the very simplest form of life that some people say isn't life at all. Let's talk about a virus. So you can talk about a virus by saying, okay, well, a virus wants to spread. It wants to propagate to the next generation. So when it infects an animal, it wants to cause a response that causes that animal to sneeze, and then the virus, having reproduced within the animal, will go out into the world in the droplets of fluid that come out from the sneeze, and will go on to infect other animals, and so the virus gets what it wants. So that's a narrative structure applied to the life cycle of the virus. I don't think that narrative is necessary. There's another way of explaining what happens as the virus propagates. It's just a sequence of chemicals connected together. And when those chemicals enter an animal's body, the animal has an immune response, which involves trying to get rid of this organism, this stretch of chemical that's infected its cells. And part of that is sneezing, producing more fluid, sneezing, just trying to get rid of it, attacking it, just trying to get it out of the body. And therefore, these chemicals propagate. It's not that the virus wants to propagate, wants to spread, wants to infect more animals. Mm-hmm. It's just what happens. So I think we need to be a little bit careful about imposing our human narratives. We're very familiar with the idea of wanting something. Yeah, I want to do this. Mm-hmm. Trying to impose that on a virus, which is just basically a chemical, we can go too far there. So
sure, absolutely. I agree. I mean, that was a lovely story, but it is a story.
Exactly. The word narrative gives it away, doesn't it? It is a narrative. And
but in the sense of if you look at even a single cell, without something maintaining homeostasis, without it being a reason to maintain homeostasis, there's not going to be any action or any movement.
Yeah, so it starts to get very philosophical here. And starts to get...
Well, it does, as far down as you go. It starts to get very philosophical.
Yeah, it starts to get the idea of purpose. Does everything that happens in the universe happen to fulfill some purpose? And that becomes a very religious idea, because mm-hmm. there's nothing in, if we get back to Wolfram physics, applying a rule to a graph that when you go up 10 to the 200 levels produces a virus that infects an animal that sneezes, that then spreads the virus. If you go back to the very lowest level, where according to Wolfram you're just applying a rule to a graph, mm-hmm. there's not any purpose there. Like, is the rule applied? Well, maybe Jordan and Peterson would say there is a purpose there, but I can't see the need for a purpose there, because just applying that rule to that graph produces 10 to the 200 levels higher this response from the animal to the virus. I don't think it's necessary to say that therefore the rule of Wolfram physics had the purpose of spreading the virus.
Yeah, I would completely agree with you there. I mean, when you start exploring that, now we're down in the weeds. And I'm not trying to attribute to Jordan Peterson any idea that there is purpose in these things at these lower levels. He's exploring, at this point with Roger Penrose, he's exploring the idea of consciousness.
Yeah.
And he's trying to understand how consciousness intersects with quantum mechanics.
Yeah.
Because that's where the questions began to come, where since the ideas of quantum physics, there's been less certainty about the universe being deterministic. There's been less certainty about the universe being completely materialistic. And that, so he's trying to explore these ideas and understand where the intersection is.
Yeah.
And that's what he's looking at. He would say that once you get to the conscious level, like a human being,
yeah,
that at any moment in time, so I'm in space right now, but there is a moment before time happens, that I'm faced with an infinite panorama of potential in front of me, infinite number of possibilities of what my next move might be. And that if I was confronted with this and could see all the possibilities and could think about all the possibilities, I'd be completely frozen. I wouldn't have any idea how to move forward, because maybe there's a field in front of me and I wouldn't have any idea how to navigate that field.
Yeah.
But that because we have a tendency as human beings to fix our eyes on some goal or some purpose, that gives us a kind of a guiding direction of how we might move in the next step. And that it's like this little thread of interest, or how, how you got interested in experimenting and wrote your first book about computers, whatever that is. The minute you have this larger purpose, it seems like things come into your field of vision that attach themselves to that purpose, and like, oh, I could look at this or I could look at that, and it gives you a little path to kind of navigate through life. But that if you don't have that thing, then you're just frozen. And when he said that, I completely understood what he meant from the standpoint, I'm a painter, so I paint pictures.
Yeah.
And when I'm faced with a blank canvas, if I'm completely free and I can just paint anything that I want, I can't paint.
Yeah.
I have to have some constraints, right? There has to be some limitation. There has to be some boundary. Necessity is the mother of invention.
Yeah, absolutely.
Right? And that's what delimits your path and gives you a trajectory to get through things.
Yeah. Well, this is fascinating, and this sort of brings us full circle back to your original question of how I lived my life. Did I have a purpose in mind? And I answered that by saying that when I was younger, I didn't particularly. I had all sorts of ideas, but I didn't have one purpose in mind, and my life has gone in all sorts of different directions. And I also mentioned that as I've got older, I'm thinking about that more. I'm at a stage where I'm in a very lucky position that I can be working on these different projects of my choosing. So I have a decision to make. Like, life isn't infinite. What do I want to work on here? And what am I best suited to work on, given my history, given all the meanderings I've done throughout my career and throughout my life? What are the things that I can really focus on here? And I very consciously thought about, okay, the two things that I have right now that fit those criteria the most, that my life so far has prepared me for, and that seem the most important if I have only 10 years of life left, say, seem to be the most important things to spend the next 10 years on are, one, Wolfram physics, because as I say, I'm in a very good position, having been, studied physics, studied mathematics, done a lot of computation, and having done a lot of writing. I'm in a very good position to explore that, and hopefully bring other people along with me at The Last Theory to explore that. And the open web mind, it's an idea I had 30 years ago now, and I've slowly worked on it through my life. Now I have a lot more time and opportunity to pursue it, and also a lot more skills based on what I've done with my career in the past to put it out there in the world. So it's fascinating what Jordan Peterson has to say about this idea of purpose within your life. I think it can be extremely powerful just to take a step back and say, okay, here's the time I've got, here's who I am and what I've been interested in and the skills that I've built up over time. What is the best thing that I can be working on right now?
Well, I hope that we can talk some more about that. I'm very excited about both projects, and I will put a link in the show notes to all of your to your website and to the Last Theory YouTube channel, and people can sign up to get emails from you.
Yes.
That with your writing about Wolfram's theory, which is,
that's right.
You know, I believe it's just a transcript of the YouTube videos, but
that's right. So yeah, if you just go to
clear.
lasttheory.com, then you can enter your email address there. And even if you just want to get the notification every couple of weeks, you can click through to the video every time the video comes out, or you can subscribe on YouTube. But yeah, my hope is that those articles will eventually come together into a book that I'll be able to publish once I understand Wolfram physics a little better.
That's great. So before we talk again next time, if you have time, it would really be great if you could watch, just in the last couple of days, Stephen Wolfram put up a working session on molecular computation where he was talking with some chemists, and some very interesting stuff came out of that working session. So if you got a chance to watch that, then we could talk about some of those molecular computational issues. And I also want to talk about time and space with you, because I think there's a lot more there. And it's one of the things that makes Wolfram's theory most interesting to me, is the way that he has a unique take on it from the most physicists. And so I think there's a lot to explore there. And he did a couple of wonderful conversations with Gregory Chaitin, who is a mathematician. And I guess they're old friends, so it was really delightful conversations anyway. But he started exploring some of these metaphysical issues with Gregory Chaitin. So it was very interesting, because I think one of the things that Wolfram realizes is that there are many deeper and wider implications to his theory than he had first considered as he goes along, and he's finding more and more of what's happening there. He's seeing a lot deeper implications. So it'd be fun to explore those.
Absolutely.
You're great fun to talk to.
That was an amazing conversation. Thank you so much, Karen. These are fascinating things to talk about, aren't they? So I really look forward to the next one.
Okay, very great. Thank you for your time.
Thanks, Karen.
Bye-bye.